Thank you for that introduction. Thank you all for attending my talk. I'm presenting this on behalf of my student, Mandana, and I still cannot, unfortunately, pronounce her last name. We call her Mandana Age, who couldn't be here today. And also, this is a collaboration with the School of Public Health at University of Illinois at Chicago. Okay. And so what I will talk to you about today actually is a larger effort that's going on at UIC in something we call the Air-Microfluidics group. And in fact, maybe some of you were trying to attend my tutorial on Sunday, and I apologize I was not able to actually make it because of some flight issues. If you're still interested in that tutorial, I believe it's going to be given tomorrow afternoon. I think there'll be an announcement about this. It's about air-microfluidics. So what I do actually is use microfluidics techniques, applying them to air quality sensors, lots of gas sensor, biodetectors, those kind of things. So basically, it's microfluidics, but it uses gas phase as opposed to liquid. That's kind of what we do. We have a research consortium. I'm just going to skip to that real quickly. It's collaboration between Argonne National Lab, UC Berkeley, and UIC, and we're kind of actively expanding. I'm just going to skip there. But anyway, it's quite interesting. We have a number of different projects. I think what's kind of very exciting, what I will talk about tomorrow, if you do happen to go to that tutorial, is a new field we're kind of starting. It's called opto-air-microfluidics. And this will be very interesting. But the bulk of our work actually is on direct mass PM sensing. So we actually build particulate matter sensors, PM 2.5, PM 4. If you've been walking around in the courtyard, you can actually see the particulate matter in the air. Those are the kind of things that we detect using resonator-based technologies. And so my talk today, this is just kind of one of our sensors. I know some of you maybe have seen this before, just kind of our microfluidic circuits. And this is on the horizon. This is kind of where we're going with this. Okay. So again, if you're interested, just a plug-in for my tutorial on air-microfluidics. That's going to be tomorrow. What I'll be talking to you about today is essentially using similar technologies, but to create miniaturized sensors for underground coal mines. And so this is actually a picture of a underground coal mine in the US. This is actually something called longwall mining. It's an amazing machine. If you have not been in a coal mine and you get a chance, I definitely encourage you to go. It's very exciting. But there is a corridor about 1,000 feet long, and there's this thing here. It's like a cheese slicer that kind of goes back and forth and just slices the coal, which then falls on a conveyor belt here and is being taken out out of the mine. Okay. The mine actually is very well ventilated because what people are worried about here is methane. Okay, so methane explosions that can propagate into float dust explosions, and we actually have a project working on some float dust detectors as well. But obviously there is dust being generated, and so we would like to make sure that these workers here are protected, and then they can measure what kind of exposure they have been exposed to. Of particular interest to NIOSH, National Institute of Safety and Health, which actually governs or decides on the limits in the United States that these workers can be exposed to, is what's called the respirable fraction of that dust. Okay, so respirable fraction is basically particles 4 micrometers or smaller that are deep enough, that are small enough that they will follow the air into our lungs. They're too big really for our immune system to handle, so they'll be sitting in the lungs. They cause impaired lung functionality, black lung disease, and also silicosis further down the line if there's silica in it. Okay, so there's a great concern for the workers not to be exposed to these things, and we would like to essentially build what you may call a radiation badge, right? So the worker can actually wear it and then determine what kind of exposure they have been, or how much of this dust they have been exposed to. I think what we see outside today, people talk more about it with respect to kind of air pollution in general, is PM 2.5, which is actually particulate matter 2.5 microns or smaller. Okay, it's a different size fraction, same thing, just this curve is a little bit shifted to the left. Okay, just to kind of bring it into context. All right, so the other thing I mentioned is silicosis. It's also important to know if there is silica in this dust. Okay, so this is actually not in the paper, but I just want to kind of point you to this, that in addition to measuring whether the dust, how much dust we actually accumulate or are exposed to, we would like to know what is it made of. Okay, so it's an additional thing that the sensor is supposed to detect. Okay, so when we were tasked to do this 2 years ago by NIOSH, they actually had a device that kind of looks like this, and this is what's used in the field today. Miners are actually wearing this. Again, if you've been into a mine, you realize that the more you carry, the more difficult is it for you to go about your tasks. There's various things that sometimes you have to climb over. But this is the state of the art right now. It's called Continuous Personal Dust Monitor. It's being used virtually by all the miners. It's kind of big, bulky, and quite expensive. Okay, so the task that we were tasked with building is a device that kind of looks like this. This is kind of still a concept drawing. It's something the size of a deck of cards. The miners can wear it, and it costs a lot less, right? So now we can essentially equip all the miners with this. They can walk around and then figure out what they have been exposed to. I think what's very interesting is, first of all, we were specifically asked not to create an optical detector because of the large variations that optical detectors have due to humidity. So the particle will actually grow a little bit, and then you're not able to actually get the actual specific mass concentration close enough to the standard for NIOSH to be able to use it. Okay, so they were actually interested in our direct mass technology. The other thing is the large dynamic range. Like I said, the mines are very well ventilated. On a good day, you might have as many particles as we have here today, probably actually less, just because of the smoke coming in from the outside. But if there is a cave-in scenario, for example, you might get so many particles you cannot see the hand in front of your face. Okay, and the sensor still has to be able to function. So that's one of the challenges. When we tricky to summarize all this in 15 minutes, but basically the stage we are at right now, or the project is still continuing, we have developed the main design for the sensor, and we're evaluating individual components and putting them together to have the entire device. So the way this is going to work is we basically have a air inlet coming into our microfluidic circuit. We decided to actually have a little bit higher flow rate, so this is not per se microfluidics. It's more a fluidic, mesoscale fluidic circuit, but there are still microfluidic components in it. Okay, so we start with an elutriator that gets rid of most of the dust. And we then have our size-selective fractionator. It's a virtual impactor. This is where we get our size-selective fraction. We specifically have the fractionator before our air preconditioning system, so that we actually get the actual fraction that the miner will be exposed to. Okay, the major flow, so which is now PM4, this is the fraction we're interested in, flows through this dryer. So interesting point, whenever we do direct mass fraction, it is also sensitive to humidity. So we want to make sure we remove the humidity according to the ISO standard. Okay, so we have some dryer, I talked about that, and then we have this kind of interesting dual fractionating mass sensor, and I'll go over that and show you how we actually can get using two resonators, one microfabricated resonator and then a slightly bigger QCM, get a uniform signal for the entire mass fraction going from 4.0 down to nanoparticles. Okay, and I'll touch a little bit on silica speciation. I'm just not sure how much time I'm going to have to do that. Okay. But some of these things, actually, again, I will go over in my tutorial. So if you're interested, I encourage you to attend it tomorrow afternoon. All right. So just kind of look at the elutriator. I don't know if you're all familiar with what an elutriator is, but basically it uses terminal velocity of particles to use size selection. So this thing uses gravity. So the air comes in here and then flows out this way. And then it's sized in such a way that the velocity here is such that particles of a certain size and above will settle down on the bottom. Okay, so we actually have this region of kind of more or less uniform velocity. And so we actually use this to get rid of larger particles, okay? So that's one of the issues with microfluidic circuits is you want to avoid fouling, right? So big particles, not good, right? So we want to make sure we eliminate them. That's what this illustrator does, okay? Then we used a virtual impactor. Normally, we actually microfabricated these for our PM sensors. In this case, because our airflow is a little bit bigger than what we're used to, we actually used conventional fabrication methods to do this. And this proved to be a little bit challenging. So you can see kind of the dimensions of our nozzle. We have to get this right to about 5% to make sure that the variability is low enough for for us to follow the ISO convention. So unfortunately, this was kind of a painful experience. I think in the future we are going to microfabricate this. But you can see here, these are actually, this is the respirable curve. These are some of the experimental points with error bars showing the standard deviation of where we are at. So we're actually quite close to the respirable curve right now, which was one of our design tasks. The tricky part, however, is we're operating in the flow regime, so we're looking at 250 milliliters per minute flow through our device, which is still small enough that some of the larger instruments do not really, we're not getting a very good signal, specifically for the minor flow. Okay, so we invented this method, and again, I'll talk about that a bit more in detail tomorrow, where we actually deposit particles on filters, we image the filters, and we can back calculate the mass deposited on the filter, and hence use something like quasi-gravimetric, we call it optogravimetric method, to determine which particles go where. Just to kind of go back here a little bit, I don't know if you're familiar with how a virtual impactor works, but most of the flow goes this way, and then a little tiny, like 10% goes this way. So most of the particles, right, most of the air goes this way, and the larger particles get ejected here, okay, and that gives us the cut point. In this case, this is designed for the respirable fraction. Okay, we have dryer, we use Nafion. As you can see here is a picture of our prototype. These basically are Nafion tubes, which basically allow permeation of water molecules. And this void here is filled with desiccant. Okay, this desiccant has to be refreshed periodically, and we see a migration of the water molecules across this membrane. And so what happens is if we have high humidity on the inlet, we actually get low humid air on the outlet, okay? And so now the particles are essentially being dried, and what we get deposited on the direct mass sensor is actual kind of mass, right? So this is actual particle without the humidity. Okay, let me go to the key point here, I think, which is how we measure the mass. Okay, so this is our actual mass sensor, and this is where the dual stud collection comes in. We have two mass sensing resonators. One is a quartz. 2 minutes, right? Yes. Okay. So I think I'm probably going to stop after this, and maybe if you are interested in silica speciation, we can talk about this after the talk, because I think otherwise I'm going to be talking for another 20 minutes. Anyway, so we use actually direct impaction to impact particles onto a QCM, and we have some preconditioning of the QCM surface. But what's kind of interesting is, so if airflow here, this is impaction, so we get some large particles on the QCM. The small ones continue this way, and then here we have our second mass sensing resonator. This is actually a MEMS device. It's an F-bar, and some of you have maybe seen this in our other publications. And we have a heater here. We create thermophoretic force and then drive the rest of the particles down onto the surface of that resonator. So the interesting effect of this is, if you look at how this actually works, is we have first the respirable fractionator, right? So that's the virtual impactor with 4 microns cut point. Okay, so basically, theoretically, we should be collecting all this mass fraction. Okay, that's what continues down through the sensor. However, because we're using impaction to collect on the first stage QCM, we also have a cut point on that one, right? So the smaller particles actually don't get impacted. So we get something like this. So this is basically the mass fraction that would be collected on the QCM. However, this is where the second stage comes in, right? So now we have a thermophoretic deposition on the MEMS resonator. This is what we've shown before in some of our previous papers. And actually it turns out the thermophoretic deposition works more favorably with smaller particle size. We can scale it. We're not depositing the entire column above the resonator. We're depositing a fraction of it, but you can scale it. So you kind of get something like this. But the interesting part is, yes, I'm just about to finish, that you basically get this overlap here, which if we kind of put these things in just the correct way, it almost matches this overlap here. So we actually get a uniform distribution at the end of the day, okay? Okay, this is just some of the results. I'm going to skip the silica speciation. And anyway, if you're more interested about this, please talk to me after the presentation. And like I said, we have a tutorial tomorrow. Yes, and maybe we have time for one question.
One question.